The press-fit automated assembly cell project was sponsored by Autocam Medical and engineered by GVSU's Senior Project Team 3. Autocam Medical is contracted to manufacture a handpiece used in cataract eye surgery. This handpiece consists of many subassemblies, including the sensor housing subassembly and the endcap subassembly. Both of these parts are manufactured with an interference fit and must be pressed together before the weld operation. Currently, Autocam Medical has one operator spend approximately 10 hours per week manually pressing these subassemblies together using an arbor press, which is a meticulous, monotonous, and time-consuming process. Therefore, we were given the task of building a machine to automate the press-fit assembly of these parts. There are 5 different sets of mating parts that our machine should be able to handle: the sensor housing subassembly and 4 different versions or part families of the endcap subassembly. The key specifications desired by Autocam Medical for this assembly cell were that it be able to preload mating parts for at least 100 assemblies, have a cycle time of 60 seconds or less for a single assembly, have a changeover time between part families of 5 minutes or less, have the ability to press to the correct depth for each subassembly as they each have different callouts on their prints, and be able to pass a capability study of 30 parts with a CPK of 1.33 or better for the sensor housing subassembly and one of the endcap subassemblies. Our automated assembly cell consists of a 3 by 5 foot vention enclosure with plexiglass panels so that the moving parts of the machine are completely contained during operation. Mechanically, we chose to use a 3-axis gantry system, tooled grippers, a servo electric press, and custom part fixturing to automate the pressing operation. The automated assembly cell is controlled by an Allen Bradley PLC and receives operator input from an HMI. The parts are preloaded by an operator into the appropriate custom trays for the set of mating parts. After loading the parts, the operator will set the appropriate program using the HMI. Once the operator sets the program on the HMI, the gantry system will pick up the female part with its first pair of grippers. Then, the gantry will move to pick up one male part with its second set of grippers. The gantry will then move both parts to the designated press location and place them onto the press fixture, placing the female part first and then the male. The press fixture resides beneath the press and is what is responsible for aligning the parts before the pressing operation. The servo electric press will then perform the press operation. The gantry will pick up the mated pair with its first set of grippers and move it back to the original location of the female part. This process is repeated for however many parts the operator loaded, with the maximum capacity of the machine being 120 part pairs. With regard to custom components, the base plate is the foundational component of our design that is directly bolted into our table. On top of the base plate are custom female and male part trays, which are removable for easy part loading. The female part trays are arranged in a 4 by 5 grid holding 20 parts each, and the male part trays are arranged in a 15 by 4 grid holding 60 parts each. The base plate was designed to hold a maximum of 6 female part trays and 2 male part trays. Other custom parts include the press fixture, which is a simplified version of the mold of the inside of the female part. This fixture orients the part at an angle so that the pressing operation can occur vertically. A tapered pin is screwed into the press fixture and controls the depth of press. If the parts were to creep out of spec, this pin allows for easy adjustment of the press depth in a single location. The grippers also have custom 3D printed jaws attached to pick up both the female and male parts. In addition, most of the custom parts were designed to have features such as tabs that prevent the parts from being loaded incorrectly, resulting in a machine fault. The 3-axis gantry was sourced from Macron Dynamics through Kendall Electric. The X and Y axes of the gantry system use a timing belt with a precision of plus or minus 1/1000th of an inch. The Z-axis uses a ball screw, increasing its precision to plus or minus 2/10,000ths of an inch. All of the axes are driven by 480-volt Allen Bradley fully encoded servo drives. The gantry can move 11.8 inches in the X direction, 35.4 inches in the Y direction, and 3.9 inches in the Z direction. The parts we are working with from Autocam Medical are very small and have very tight tolerances, typically 1/1000th of an inch or less, so this gantry system was chosen for its high precision, allowing it to properly move and orient the parts onto the press fixture. Our automated assembly cell uses small part grippers sourced from Shunk, with custom 3D printed carbon fiber nylon jaws to grip and pick up the parts. These grippers were chosen as they are made specifically for small parts, have a positional repeatability of plus or minus 8/10,000ths of an inch, and have an opening and closing time of 0.09 seconds. Preliminary testing was completed on Autocam Medical's current arbor press to approximate the amount of force needed to press endcap subassemblies together and sensor housing subassemblies together. It was found that a force of less than 191 pounds was needed in order to press but not crumple the nozzle endcap, which requires the least amount of force to assemble. The testing also concluded that a force of 224 pounds is needed to successfully press together the sensor housing subassembly. Therefore, we selected a 24-volt servo-electric screw press sourced from IAI for our automated assembly cell. This press has a press force range from 45 to 450 pounds and can provide both positional and force feedback, ultimately allowing us to successfully press each of the 5 sets of mating parts together without damage, satisfying our primary machine specification from Autocam Medical. With regards to the control portion of this project, we designed a 4-row control panel with proper spacing between components to allow for airflow. Our automated assembly cell is a 480-volt 3-phase system that uses a 600-volt 30-amp disconnect. As shown, there are 3 fuses, one for each phase. The 480 volts for the panel comes in from the disconnect and is distributed to 2 different circuit breakers, one for the servo drives and the other for the power supply. The power supply converts the 480 volts AC to 24 volts DC, which is the required voltage of all of the controlled devices in the panel. Each controlled device has a circuit breaker rated based on the current it draws. For example, a 1-amp circuit breaker is used for the PLC and a 3-amp circuit breaker is used for the HMI. For this assembly cell, we used a compact Guard Logic 5380 Allen Bradley safety PLC. In addition to the PLC, we also utilized 1 digital input card and 1 digital output card that each have 16 channels. All controlled devices are Ethernet IP connected with the PLC through an Ethernet switch, with the exception of the grippers, which are connected to the output card of the PLC. Moreover, we have simple devices such as the start and stop buttons on the HMI pendant, sensors for the grippers, and stack lights that are connected to the I/O cards connected to the PLC. The gantry is driven by Allen Bradley 480-volt 4500 RPM servos. These servos are equipped with 18-bit batteryless absolute encoders, which are crucial in determining and programming the 244 distinct locations in our project. These servos are driven by Allen Bradley 5500 kinetic servo drives, which are daisy chain connected within the panel and communicate with the PLC over Ethernet. Our Ethernet safety PLC allows for Ethernet safe torque off integration, and these drives have over-travel limit switches directly wired, which will protect the servos and gantry system in the event of an unforeseen error. The PLC controlling the machine has been programmed with ladder logic. The 2 main control functions used in the programming of this machine are the multi-axis move and multi-axis jog commands. The multi-axis move command allows us to command the gantry to move to an absolute position based on the set home position, or incremental distance moves. The multi-axis jog command allows for simple directional control and is what commands the manual mode of our machine. The IAI servo-electric press chosen for this project came with its own press controller that communicates with the PLC over an Ethernet connection. The press controller has a dedicated e-stop control bit and is also independently able to pull power out of the servo, allowing faults to be programmed to protect the press and custom press fixturing within the assembly cell should an accident or error occur. Other safety control features of our automated assembly cell include the Allen Bradley Guard Link, which is an Ethernet safety input device. The Guard Link supports the traditional e-stop button on the HMI pendant and the electromechanical door safety switch that prevents the operator from putting the machine in automatic mode with the door open. Our testing procedure will occur in 4 parts. The first part of the testing is the fault state and recovery testing. This testing involves forcing the machine into faults and ensuring that all components stop moving, the stack light turns on indicating a fault, and the HMI indicates the faulted state. This stage of testing has already been completed. The second stage of testing focuses on the changeover time. The press tool, press fixture, female jaws, and male jaws must be switched during this time. The current specification is that this process take 5 minutes or less. Next, the single part cycle time will need to be verified at 1 minute or less. This can be easily checked on the HMI display on the home or automatic mode screens. The last stage of testing will involve completing a capability study on the sensor housing subassembly and one endcap part family subassembly. Each capability study will be run on 30 sets of mating parts. The feature the capability study will test is the length of the stream relief or irrigation connector left outside of the endcap or connector block and will be measured on a Keyence vision system. Minitab software will be used to get the machine capability data and complete the study. A CPK value of 1.33 or better is required for the automated assembly cell to be considered capable. Thank you for taking the time to view this video. Special thanks to Chris Colleen, Dan Turolva, Dr. Pung, and Jared Bergeron for their guidance on this project.